Regular primes may be defined via the divisibility of either class numbers or of Bernoulli numbers. The first few regular odd primes are 3, 5, 7, 11, 13, 17, 19, 23, 29, 31, 41, 43, 47, 53, 61, 71, 73, 79, 83, 89, 97, 107, 109, 113, 127, 137, 139, 151, 163, 167, 173, 179, 181, 191, 193,197, 199. Definition. Class number criterion. An odd prime number P is defined to be regular if it does not divide the class number of the pth cyclotomic field Q. Where zeta p is a pth root of unity, it is listed on A000927. The prime number 2 is often considered regular as well. The class number of the cyclotomic field is the number of ideals of the ring of integers Z up to isomorphism. Two ideals I, J are considered isomorphic if there is a non-zero U in Q so that I equals UJ. Kummer's criterion. Ernst Kummer showed that an equivalent criterion for regularity is that P does not divide the numerator of any of the Bernoulli numbers Bk for k equals 2, 4, 6, p-3. Kummer's proof that this is equivalent to the class number definition is strengthened by the Herbrand-Ribet theorem, which states certain consequences of P dividing one of these Bernoulli numbers. Seagulls Conjecture. It has been conjectured that there are infinitely many regular primes. More precisely, Carl Ludwig Siegel conjectured that E-1/2, or about 60.65%, of all prime numbers are regular, in the asymptotic sense of natural density. Neither conjecture has been proven to date. Irregular primes. An odd prime that is not regular is an irregular prime. The first few irregular primes are 37, 59, 67, 101, 103, 131, 149, 157, 233, 257, 263, 271, 283, 293, 307, 311, 347, 353, 379, 389, 401, 409, 421, 433, 461, 463, 467, 491, 523, 541. 547,557, 577, 587, 593. Infinitude K. L. Jensen proved in 1915 that there are infinitely many irregular primes of the form 4n+3. In 1954 Karlitz gave a simple proof of the weaker result that there are in general infinitely many irregular primes. Metz-Sankila proved that for any integer t greater than 6, there are infinitely many irregular primes not of the form mount +1 or mount -1. Irregular pairs. If P is an irregular prime and P divides the numerator of the Bernoulli number B2k for 0 less than 2k less than P-1, then is called an irregular pair. In other words, an irregular pair is a bookkeeping device to record, for an irregular prime P, the particular indices of the Bernoulli numbers at which regularity fails. The first few irregular pairs are the smallest even k such that nth irregular prime divides bk of 32, 44, 58, 68, 24, 22, 130, 62, 84, 164, 100, 84, 20, 156, 88, 292, 280, 186. 100,000, 200, 382, 126, 240, 366, 196, 130, 94, 292, 400, 86, 270, 222, 52, 90, 22. For a given prime P, the number of such pairs is called the index of irregularity of P. Hence, a prime is regular if and only if its index of irregularity is 0. Similarly, a prime is irregular if and only if its index of irregularity is positive. It was discovered that is in fact an irregular pair for P equals 16,843, as well as for P equals 2,124,679. There are no more occurrences for P less than 109. Irregular index. An odd prime P has a regular index n if and only if there are n values of k for which P divides B2k and these k's are less than 2. The first irregular prime with a regular index greater than 1 is 157, which divides B62 and B110, so it has an irregular index 2. Clearly, the irregular index of a regular prime is 0. The irregular index of the nth prime is 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 1, 0, 0, 0, 0, 0, 0, 1, 1, 0, 0, 0, 0, 1, 0, 0, 1, 0. 2, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 0, 1, 1, 0, 1, 0, 0, 1, 1, 1, 1, 0, 0, 0, 0, 1, 0, 2, 0. The irregular index of the nth irregular prime is 1, 1, 1, 1, 1, 1, 1, 2, 1, 1, 1, 1, 1, 1, 1, 1, 1, 2, 2, 1, 1, 1, 1, 1, 1, 1, 2, 3, 1, 1, 2, 1, 1. 2, 1, 1, 1, 3, 1, 2, 3, 1, 1, 2, 1, 1, 2, 1, 1, 1, 1, 1, 1, 2, 1, 1, 1, 1, 1, 1, 1, 2, 1, 1, 1, 1, 1, 1, 3, 1, 1, 1. The primes having a regular index 1 are 37, 59, 67, 101, 103, 131, 149, 233, 257, 263, 271, 283, 293, 307, 311, 347, 389, 401, 409, 421, 433, 461. 463,523, 541, 557, 577, 593, 607, 613, 619, 653, 659, 677, 683, 727, 751, 757, 761, 773, 797, 811, 821, 827, 839, 877, 881, 887, 953, 971. The primes having a regular index to are 157, 353, 379, 467, 547, 587, 631, 673, 691, 809, 929, 1291, 1297, 1307, 1663, 1669, 1733, 1789, 1933, 1997, 2003, 2087, 2273, 2309, 2371, 2383, 2423, 2441, 2591, 2671, 2789, 2909, 2957. The primes having a regular index 3 are 491, 617, 647, 1151, 1217, 1811, 1847, 2939, 3833, 4003, 4657, 4951, 6763, 7687, 8831, 9011, 10463, 10589, 12,073, 13,217, 14,533, 14,737, 14,957, 15,287, 15,787, 15,823, 16,007, 17,681, 17,863, 18,713, 18,869. The least primes having a regular index n are 2, 3, 37, 157, 491, 12,613, 78,233, 527,377, 3,238,481. Euler irregular primes. Similarly, we can define an Euler irregular prime as a prime p that divides at least one E2n with 0 to np minus 3. The first few Euler irregular primes are 19, 31, 43, 47, 61, 67, 71, 79, 101, 137, 139, 149, 193, 223, 241, 251, 263, 277, 307, 311, 349, 353, 359. 373,379, 419, 433, 461, 463, 491, 509, 541, 563, 571, 577, 587. The Euler irregular pairs are. Van Diver proved that Fermat's last theorem has no solution for integers x, y, z with GCD equals 1 if P is Euler regular. Gut proved that x2p plus y2p equals z2p has no solution if P has an irregularity index less than 5. It was proven that there is an infinity of irregular primes. A stronger result was obtained. There is an infinity of irregular primes congruent to 1 modulo 8. As in the case of Kummer's b-regular primes, there is as yet no proof that there are infinitely many irregular primes, though this seems likely to be true. Like b-irregularity, irregularity relates to the divisibility of class numbers of cyclotomic fields. Strong irregular primes. A prime P is called strong irregular if P divides the numerator of E2n for some 0n less than, and P also divides E2n for some 0n less than, where Bn is the Bernoulli number and n is the Euler number. The first few strong irregular primes are 67. 101,149, 263, 307, 311, 353, 379, 433, 461, 463, 491, 541, 577, 587, 619, 677, 691, 751, 761, 773, 811, 821, 877, 887, 929, 971, 1151, 1229, 1279, 1283, 1291, 1307, 1319, 1381, 1409, 1429, 1439. To prove the Fermat's last theorem for a strong irregular prime P is more difficult. The most difficult is that P is not only a strong irregular prime, but 2P plus 1, 4P plus 1, 8P plus 1, 10P plus 1, 14P plus 1, and 16P plus 1 are also all composite. The first few such P are 263,311, 379, 461, 463, 541, 751, 773, 887, 971, 1283. Weak irregular primes. A prime P is weak irregular if and only if P divides the numerator of B2n or E2n for some 0n less than, where Bn is the Bernoulli number and n is the Euler number. The first few weak irregular primes are 19, 31, 37, 43, 47, 59, 61, 67, 71, 79, 101, 103. 131,137, 139, 149, 157, 193, 223, 233, 241, 251, 257, 263, 271, 277, 283, 293, 307, 311, 347, 349, 353, 373, 379, 389, 401, 409, 419, 421, 433, 461, 463,491, 509, 523, 541, 547, 557, 563, 571, 577, 587, 593. The first values of Bernoulli and Euler numbers are 1, 1, 1, 1, 1, 5, 1, 61, 1, 1385, 5, 50,521, 691, 2,702,765, 7, 199,360,981, 3,617, 19,391,512,145, 43,867. 2,404,879,675,441, 174,611, 370,371,188,237,525, 854,513, 69,348,874,393,137,901, 236,364,091, 155145341635570869005, 8,553,103, 408702509293123892361, 23,749,461,029. 1252259641403629865468285. We can regard these numbers as the numerator of the generalized Bernoulli numbers chapter 1, 1, 1, 3, 1, 25, 1, 427, 1, 12,465, 5, 555,731, 691, 35,135,945. 7, 2,990,414,715, 3,617, 329,655,706,465, 43,867, 45,692,713,833,379, 174,611, 1,111,113,564,712,575, 854,513, 1595024111042171723, 236,364,091, 387863354088927172625, 8,553,103, 11,553,575,095,745,093,747, 23,749,461,029. And generalized Euler numbers chapter 1, 1, 1, 1, 2, 5, 16, 61, 272, 1385, 7,936, 50,521, 353,792, 2,702,765, 22,368,256, 199,360,981, 1,903,757,312, 19,391,512,145. 209,865,342,976, 2,404,879,675,441, 29,88,185,112,832, 370,371,188,000,188 8,237,525, 4,951,498,053,124,096, 69,348,874,393,137,901, 1015423886506852352 1551441635557086905 2469214801902079836164 408707259293123892361 7025160160394395988787 1252259641403629865468285. In fact, if we let Bn be the nth generalized Bernoulli number, n be the nth generalized Euler number, then weak irregular pairs th Euler number if n is odd, since for every odd prime p divides ap if and only if p is congruent to 1 mod 4, and since p divides the denominator of th Bernoulli number for every odd prime p, so for any odd prime p cannot divide ap 1. Besides, if and only if an odd prime p divides m, then p also divides n plus k does not divide n. Then p divides m for every integer k must be greater than 1. For example, since 19 divides a11 and 2 times 19 equals 38 does not divide 11, so 19 divides a18k plus 11 for all k. Thus, the definition of a regular pair, n should be at most p2. The following table shows all irregular pairs with odd prime p. 661. The only primes below 1000 with weak irregular index 3 are 307, 311, 353, 379, 577, 587, 617, 619, 647, 691, 751, and 929. Besides, 491 is the only prime below 1000 with weak irregular index 4, and all other odd primes below 1000 with weak irregular index 0, 1, or 2. The following table shows all irregular pairs with n63. C. The following table shows irregular pairs. It's a conjecture that there are infinitely many irregular pairs for every natural number n2, but only few were found for fixed n. For some values of n, even, there is no known such prime p. Harmonic irregular primes a prime p such that p divides hk for some 1k p2 is called harmonic irregular primes always divides hp1, where hk is the numerator of the harmonic numbers. The first of them are 11, 29, 37, 43, 53, 61, 97, 109, 137, 173, 199, 227, 257, 269, 271, 313. 347,353, 379, 397, 401, 409, 421, 433, 439, 509, 521, 577, 599. The density of them is about 0.367879, very close to that of B irregular or irregular primes. The numerator of the harmonic numbers are 0, 1, 3, 11, 25, 137, 49, 363, 761, 7129, 7381, 83711, 86021, 1,145,993, 1,171,733, 1,195,757, 2,436,559. 42,142,223, 14,274,301, 275,295,799, 55,835,135, 18,858,053, 19,093,197, 444,316,699, 1,347,822,955, 34,052,522,467, 34,395,742,267, 312,536,252,003, 315,404,588,903, 9,227,046,511,387. The harmonic irregular pairs are, in fact, if and only if a prime P divides HK, then P also divides HP1K, so all odd prime P have an even harmonic irregular index. The super-irregular primes are 353, 379, 433, 577, 677, 761, 773, 821, 929, 971. The super-regular primes are 3, 5, 7, 13, 17, 23, 41, 73, 83, 89, 107, 113, 127, 151, 163, 167, 179, 181, 191, 197, 211, 229, 239, 281, 317, 331. 337,367, 383, 431, 443, 449, 457, 479, 487, 503, 569. History. In 1850, Kummer proved that Fermat's last theorem is true for a prime exponent P if P is regular. This raised attention in the irregular primes. In 1852, Janicki was able to prove that the first case of Fermat's last theorem is true for an exponent P if is not an irregular pair. Kummer improved this further in 1857 by showing that for the first case of Fermat's last theorem it is sufficient to establish that either or fails to be an irregular pair. Kummer found the irregular primes less than 165, although the two latter tables did not appear in print. Johnson found that is in fact an irregular pair for P equals 16,843 and that this is the first and only time this occurs for P less than 30,000. It was found in 1993 that the next time this happens is for P equals 2,124,679, see Wollaston-Holm prime.